Good morning to all. I am Geeta, Assistant Professor from ECE Department, Rohini College of Engineering and Technology. I am going to handle the subject on Communication Engineering. So now I am going to discuss about the topic on differential pulse code modulation. On completion, the students will be able to define differential pulse code modulation, draw the block diagram of DPCM transmitter and draw the block diagram of DPCM receiver. So differential pulse code modulation. So we are having the successive samples or carrying the same information with little difference when the samples are encoded by standard PCM system. So the resulting encoded signal will be contain the redundant information. By removing the PCM information redundancy is more efficient coded signal may be obtained. This is done using the differential pulse code modulation. So the principle is based on the differential pulse code modulation is linear prediction. So we have to define the differential pulse code modulation, that is the difference in the amplitude of two successive samples that transmit a rarer than actual value. So the present value is predicted by a linear combination of the past sample values. So the error is computed between original and predicted samples. Here the error signal is small when compared to the original one. So the less bits are required to encode the bits. So in the DPCM transmitter, the information signal M of t is sampled at a rate of Fs, that is the sampling frequency, to produce the sampled signal M of nTs. But Ts is the interval between the adjacent samples. So this is the DPCM transmitter block diagram, that is we are having the sampled input, that is M of nTs, then we are having the comparator, then this will be connected to the quantizer, that is E of nTs, that is the error signal, then EQ of nTs, this will be connected to the encoder. So in the down we are having the M cap of nTs, this will be connected to the comparator. In the down we are having the prediction filter, that is MQ of nTs. Finally we will get the output as the DPCM wave. The predictor filter produces a predictor version of the sampled input and the predictor output. This will be defined by M cap of nTs. The input signal is quantized and it is defined by E of nTs will be equal to M of nTs minus M cap of nTs. So we have to calculate the prediction error, that is E of nTs will be called as the prediction error signal, because if represent the difference between the unquantized input sample M of nTs and the prediction value M cap of nTs. The quantizer output must be expressed as EQ of nTs will be equal to E of nTs plus Q of nTs, where Q of nTs is the quantization error and E of nTs is the prediction error. So the input of the prediction filter is, that is MQ of nTs will be equal to M cap of nTs plus EQ of nTs. So now we have to substitute the equation 1 in equation 2, where MQ of nTs will be equal to M cap of nTs plus E of nTs plus Q of nTs. So by using equation 1, the equation 4 is MQ of nTs will be equal to M of nTs plus Q of nTs. Therefore, the quantized sample MQ of nTs at the prediction filter, the input will be differs from the original sample value, that is M of nTs, by quantized error Q of nTs. So the quantization error can be negative or positive. Then differential pulse code modulation receiver. So the quantized error signal is EQ of nTs is reconstructed from the incoming barrier signal, that is differential pulse code modulation by a decoder block. So this is the diagram for the DPCM receiver. First we are having the DPCM signal. This will be given to the decoder. Then we are having the comparator, that is EQ of NTS. Down we are having M cap of NTS. This will be connected to the prediction filter. Finally we will get the output as the original signal. The quiz question is based on differential pulse code modulation. In differential pulse code modulation techniques, the decoding is performed by dash. Thank you.